All right, so you know why you're here, right? You love learning about complex topics, but you don't want to sift through mountains of dense research.
Yeah, you want that knowledge fast and clear.
Yeah.
No jargon overload, right?
Exactly. That's what the deep dive is all about, becoming well-informed effortlessly. Think of it like a shortcut to expertise.
A fast track.
Exactly.
Hmm.
And today we're tackling something pretty fascinating, how scientists are changing the game when it comes to modeling materials.
Modeling how they behave under extreme conditions. We're talking high-speed impacts, explosions, that sort of thing.
Yeah, the kind of forces you see in a high-speed car crash or, like you said, something exploding. Crucial stuff if we're talking, designing safer vehicles
Yeah.
or better protective gear.
Absolutely. Think about it. Imagine you're trying to predict what happens when a new type of armor gets hit by a projectile. That kind of simulation, it's vital for both safety and innovation.
Right, makes sense.
But there's a challenge, a big one, and it's at the heart of the research we're diving into today.
Oh, and what's that?
Finding that perfect balance between a model's accuracy and how fast it can actually give us an answer.
Ah, so like you can have a super detailed model that takes forever to run.
Right.
Or you got a really quick and dirty one that misses all those important fine points.
Exactly, a real balancing act. And that's where this new approach comes in, something called HYDRA.
HYDRA, like the mythical serpent.
Exactly, the one with all those heads. And they name it that for a reason. Flexibility is key here.
Okay, I'm intrigued. So this HYDRA is an algorithm.
A new learning algorithm, yep. It's aiming to give us the best of both worlds, accurate predictions about how a material will behave.
But without all that computational overhead.
Yeah.
The stuff that slows down those complex models.
Precisely.
Got it. So we're diving deep into HYDRA today, figuring out how it pulls this off, why it's causing such a stir in the scientific community, and what it can do.
Especially when it comes to modeling materials like, the explosive beta HMX.
Beta HMX, got it.
And even something as seemingly simple yet incredibly complex as diamond.
Diamond, huh? Okay, so where do we even begin with something like this? What's the core problem that HYDRA is tackling?
It all boils down to this fundamental trade-off in material modeling. How expressive a model is. That's its ability to really capture complex behaviors versus how quickly it can make those predictions. That's what we call its inference time.
Inference time.
Yeah.
Okay, so like how long it takes to churn out an answer.
Exactly. And this is especially important for those simulations called hydrocodes.
Hydrocodes. Now, those are specifically for modeling these really extreme events.
Precisely. Think shockwaves ripping through a material.
Okay, yeah. Those are definitely high-stakes scenarios.
Exactly. So these simulations, what they do is break down a material into countless tiny points. And then they simulate how all those points interact over incredibly short time intervals.
So if the model that's controlling how each of these points behaves is slow to calculate,
the whole simulation grinds to a halt. We could be talking days or even weeks of runtime.
oh wow, so speed is of the essence.
Absolutely critical.
So what were the go-to methods for building these material models before HYDRA came onto the scene?
Well, there were a couple of main paths. Our sources highlight those pretty clearly.
Okay, let's hear them.
So first you had what we call handcrafted models. These were built on those well-established physics principles. Material science, often expresses pretty straightforward math equations.
Okay, so the advantage there, I'm guessing, is speed.
Exactly. They can be evaluated super quickly, which is what you need for hydrocodes. But there's a catch. Because they rely on those predefined relationships, sometimes they lack the sophistication to truly represent how some materials act under extreme stress. They might miss those subtle but crucial nuances.
Ah, so they're fast, but maybe not quite smart enough for those really tricky situations.
Yeah, that's a good way to put it.
What's the other approach then?
That's where neural networks step in.
Ah, neural networks. Okay, so we're getting into the AI side of things.
Exactly. These are those powerful machine learning tools that can learn incredibly complex patterns from mountains of data. So in theory, a really well-trained neural network could capture all those intricate material behaviors.
The ones that those handcrafted models might miss.
Exactly. But the catch, and we've touched on this, is that as these networks get larger and more complex, with tons of those interconnected processing units or neurons, the more computationally expensive they become, leading to that dreaded slow inference time.
Right back to that bottleneck. And I know there have been attempts to speed up neural networks, right? Things like pruning.
Oh, absolutely. Techniques like pruning are aimed at making those networks more efficient.
So the idea there is you identify and remove the parts of the network that aren't contributing much to the accuracy.
Exactly. You're essentially slimming down the model,
Yeah.
reducing the number of calculations you need.
Okay, so you trade a bit of accuracy for speed.
Yeah, that's the trade-off. You're sacrificing some of the model's ability to really capture those super complex behaviors.
So we're stuck between a rock and a hard place. Fast, but potentially too simplistic. Or maybe super accurate, but incredibly slow. How does HYDRA offer a way out of this dilemma? What's its secret sauce?
HYDRA is a two-step process. It's really ingenious. So instead of trying to directly force a neural network to be faster, or just sticking with those predefined equations, it uses a neural network to learn a really accurate model of the material's behavior first.
Okay, so step one, use the neural network to build a really good model. And then what?
Then it takes that learned model and transforms it into an actual symbolic mathematical equation.
Wait, hold on. It turns a neural network into an actual readable equation. That sounds kind of like science fiction.
It is pretty remarkable, and that's what makes HYDRA so unique.
So how does that even work? Can we break down that two-step process, starting with step one? What's going on there?
All right, so step one involves training a specific type of neural network. It's called a neural additive model, or a NAME. But there's a twist. Instead of trying to model the material's response in its raw, complex form, we're talking about what's technically called the ambient strain space. HYDRA first uses a data-driven approach to project this complex information onto something simpler, something we call a hyperplane.
Hyperplane.
Yeah, think of it like this. You're looking at this multifaceted object, but you find just the right angle to view it from.
And suddenly it all makes sense.
Exactly. It reveals all those underlying symmetries and simpler structures, and that's what this projection does. It's a mathematical transformation, essentially reorienting and scaling the data.
So it's finding the right perspective to make this really complex problem more manageable.
Exactly. And what's really cool is that this projection isn't preset, it's learned from the data itself, alongside the NEM. So it figures out the best way to simplify things while still keeping all that crucial information about the material's behavior.
So it's not just about simplifying, it's about simplifying intelligently. Okay, and you mentioned this neural additive model. What makes it stand out from your typical neural network?
Most of those deep learning networks are often called black boxes because it's tough to really understand how they reach their predictions.
Right, they just spit out an answer.
Exactly. But an M is more transparent. It models a function as a sum of individual functions, where each of those individual functions only looks at one of the input variables.
Or in HYDRA's case, one of those projected variables.
Right. So it's like breaking down a really complex task into a bunch of simpler independent tasks, and then you just combine the results.
Okay, that makes it way more understandable. You can actually see how each projected feature is contributing to the overall prediction.
Exactly.
So look at this straight. HYDRA takes this incredibly complex material behavior, simplifies it by looking at it from this learned perspective, that's the projection, and then models it as a combination of simpler individual relationships within that perspective using an AM.
You got it.
Okay, that's step one. Now, how do we get from this trained NAM in its projected space to a nice, neat symbolic equation? That's step two, right?
Step two is where the magic happens. It involves this powerful AI technique called symbolic regression, or SR.
Symbolic regressions. So what's that all about?
Unlike regular machine learning, where you're just trying to find those numerical values for parameters, symbolic regression takes things further. It actually searches for the mathematical equation itself, the formula that best describes the data.
Wow. So it's not just crunching numbers, it's trying to uncover the underlying relationship.
Exactly. It can figure out the actual form of that relationship using all sorts of operations: addition, subtraction, multiplication, division, exponentials, logarithms, trigonometric functions, whatever fits best.
So it's like an AI mathematician.
Yeah.
Trying to rediscover the laws of physics just from the data. That sounds computationally intense.
It can be. If you try to apply symbolic regression directly to that original high-dimensional strain space, it's a nightmare. A really tough problem to crack. What's called NP-hard, technically.
NP-hard. So like virtually impossible.
Pretty much. But HYDRA sidesteps that. It applies symbolic regression to each of those individual feature functions that the NAM learned in that simpler projected space.
Ah, so because the NAM has already untangled those complex relationships.
Exactly. And remember, those are now single variable functions. So finding a symbolic expression for each of those is way easier than trying to find one massive complex equation in that original messy high-dimensional space.
Makes sense. It's like solving a bunch of small puzzles instead of one gigantic one.
A perfect analogy.
So what do we get at the end of this whole two-step process? What's the final result?
We end up with what's called a hyperelasticity model. It's essentially a mathematical description of how a solid material deforms and stores energy elastically, and it's expressed as a nice, clean, symbolic mathematical equation.
So a real equation that scientists can actually read and understand.
Exactly. And because it's a relatively compact equation, a computer can process it super quickly. That gives us that fast inference time we need for those hydrocode simulations.
So it's like having the speed of those handcrafted models, but with the potential for much higher accuracy because it was learned from data using a neural network.
You nailed it. The best of both worlds.
Impressive.
Mm-hmm.
But it sounds like the advantages go beyond just speed and accuracy.
Oh, absolutely. There's a lot more to unpack here. Because the model is in this symbolic form, a real equation scientist can easily analyze its properties. They can even do something called symbolic differentiation, super useful for those more advanced calculations within hydrocodes. And it can even help reduce memory usage.
Wow, so it's efficient on multiple levels.
It is.
Okay, so all of this sounds amazing in theory, but what kind of real-world results has HYDRA actually demonstrated?
Our sources highlight some pretty impressive capabilities. First off, there's dimensionality reduction.
Dimensionality reduction, what's that?
So for simpler materials, ones that behave the same way in all directions, those are called isotropic materials.
Isotropic, got it.
HYDRA could automatically simplify the problem by taking those 6 components that usually describe strain and projecting them onto a lower dimensional space, sometimes just 2 or 3 dimensions, all without really sacrificing accuracy.
So it's like the algorithm is realizing, hey, this problem isn't actually as complicated as it seems.
Exactly. It's learning those inherent symmetries in the material's behavior and ditching any redundant information.
That's pretty cool.
But it gets even more interesting. For more complex materials, like those cubic diamond crystals and monoclinic beta HMX.
The ones that have different properties depending on which direction you look at them from.
Exactly. They're called anisotropic materials.
Anisotropic, right?
The researchers found that projecting the strain data onto a higher dimensional feature space actually boosted the accuracy significantly compared to using a standard NAM directly.
Hold on. So you're saying that for those really intricate materials, sometimes you need to look at them from even more perspectives.
Counterintuitive, right?
Yeah, it seems like adding more dimensions would make things more complicated, not less.
You'd think so. But the results are there. It works. In the case of Diamond, they actually used a NAM operating in a 12-dimensional projected space.
12 dimensions.
Yeah, and it actually outperformed a classic, fully connected neural network in terms of accuracy on some tasks. Pretty remarkable.
So it's not just about speed. Sometimes it's actually more accurate than those traditional deep learning approaches. That's huge. But what about that all-important inference time? How fast are these symbolic models that HYDRA generates?
The research directly compares the speed of HYDRA symbolic models with comparable neural network models, and the symbolic models were consistently and significantly faster.
How much faster are we talking?
In that diamond crystal example, they saw speed-ups from 200% to 300% or even more, all while maintaining or even improving accuracy.
Wow, those are some serious speed gains.
It's a game changer.
Can you give me a real-world sense of what that kind of speed-up translates to?
Absolutely. So for that beta HMX material, the symbolic model created by HYDRA only needed a few hundred basic arithmetic operations to make a prediction about how it would behave under stress.
Okay, a few hundred. That doesn't sound like much.
It's not. But a neural network that achieved a similar level of accuracy needed tens of thousands of operations for the same prediction.
Tens of thousands versus a few hundred. That's a massive difference.
And when you're running simulations that involve millions or even billions of these calculations...
That kind of efficiency gain is a game changer.
Absolutely. It turns simulations that were previously impractical into something you can actually run.
That could really accelerate research and development in so many fields.
It has the potential to.
So we've got the speed, we've got the accuracy. What other advantages did HYDRA showcase?
Another great finding was how robust HYDRA is to noisy data. So the researchers intentionally added noise to some synthetic data for Diamond.
Okay, so they're introducing errors into the data
Exactly. And the symbolic models that HYDRA created were much more stable and physically plausible when making predictions outside the training data range compared to the neural network it was based on.
So even when fed imperfect data, HYDRA still produced reliable models.
Yeah, it seems like that symbolic regression process has a kind of filtering effect, leading to more robust models.
That's really important for real-world applications where data is rarely perfect.
It is. Now, for the beta HMX material, they use data from really high-fidelity molecular dynamics simulations.
So simulations that are already very accurate and obey the laws of physics at the atomic level.
Right. And the symbolic model that HYDRA created it actually captured some really important physical constraints implicitly.
Implicitly, meaning it wasn't explicitly programmed into the algorithm.
Exactly. It learned those constraints just from the data itself.
Wow, so what kind of constraints are we talking about?
Well, for example, it automatically figured out material frame indifference.
Yeah.
That basically means the model's predictions stay consistent no matter how the observer is moving or oriented.
Okay, that makes sense.
It also learned the inherent material symmetry of that beta HMX crystal structure. And get this, it even learned the growth condition in compression, which is a fundamental principle in physics. The idea that the energy of a material skyrockets as you squeeze it down to zero volume.
So it's rediscovering these fundamental physical laws just by looking at the data.
It is. It's pretty remarkable. And because the model is in that symbolic form, the researchers could also perform stability analysis way more efficiently. Calculate things like those tangent stiffness tensors. You know, the things that help predict when a material might buckle under pressure.
Okay, and this is all thanks to HYDRA's unique approach.
Exactly. And to top it off, when they used the learned model to simulate shock loading in beta HMX, it clearly showed the material's anisotropic behavior, how it reacts differently depending on the direction of the impact. You know, a key trait of this material.
So HYDRA is not just fast and accurate. It's interpretable, robust, and it can even learn fundamental physics. That's a huge deal for material modeling. Were there any particular moments in the research that really stood out to you, like those aha moments?
Definitely. That counterintuitive finding about projecting onto a higher dimensional space to actually simplify things for complex materials, that was a big one.
So sometimes you need to add more dimensions to make things simpler.
It really challenges our intuition. It highlights the importance of finding that perfect representation of the data.
We have the right perspective.
And combining neural networks with symbolic regression, that's elegant.
Yeah.
Using AI to learn patterns and then translate that knowledge into math, into an equation that's both human readable and computationally efficient.
That fusion is really powerful.
And the fact that it can pick up on those fundamental physical laws just from the data, that opens up a whole new world of possibilities for scientific discovery. We can potentially uncover hidden relationships that we might have missed otherwise. And of course, the sheer speed improvements for these crucial simulations. That's transformative for any field that needs to understand how materials behave under pressure.
From designing safer cars to maybe even creating more efficient energy storage solutions, the applications are far-reaching.
They are.
So to wrap things up, HYDRA is a truly groundbreaking algorithm. It blends neural networks and symbolic regression to create material models that are fast, accurate, interpretable, and even capable of learning physics implicitly.
A great summary. It really gets to the heart of why this research is generating so much excitement.
So for you, the listener, who's always eager to learn about the latest advancements, this deep dive gives you a solid understanding of a cutting-edge technique in material modeling, a technique that's pushing the boundaries of what's possible.
And it begs the question. Given HYDRA's success in this domain, where else could this hybrid approach be applied? What other complex problems in science and engineering could benefit from this blend of AI and symbolic knowledge?
Right. Could we see similar algorithms popping up in fields like fluid dynamics or combustion modeling? Maybe even in climate science or drug discovery.
It really makes you think about the possibilities, how we can bridge the gap between the learning power of AI and the clarity and efficiency of those classical mathematical models.
Definitely food for thought. Now, if you're itching to explore this in more detail, we highly recommend checking out the original research paper. It's published in Computer Methods in Applied Mechanics and Engineering.
And for those who like to tinker, the open source code for HYDRA is available on GitHub. You can find it at github.com/NTA fan7hydra. We'll drop a link in the show notes too.
Perfect. And as you delve deeper into all of this, think about the questions that are probably driving the next wave of research. What are the limitations of this approach? How do those specific choices made during the model building process impact the final outcome? And how well can HYDRA handle even more complex materials or even larger data sets?
Those are the challenges that will shape the future of this exciting field.
Absolutely. Well, that wraps up our deep dive into HYDRA. Thanks so much for joining us. We hope this has been an insightful journey into the world of computational material science. Until next time, keep those curious minds engaged and never stop exploring.
And keep asking those deep questions.
Absolutely.